Welcome to the fifth of our differential geometry class. Last time I finished section 5.1, which was study of surfaces, but yeah, we defined shape operator last time. At the end of the section, there was a lemma. I didn't have time to state it, so let me just start by stating that lemma. The proof of the lemma will be postponed because it is not that easy. We will later have some tools to prove that. Let me just state the lemma. For any point P on a surface M, the shape operator, the shape operator S, which is defined from the tangent space to itself, is symmetric. So that's a important fact. What we mean by that, let me just write it more, giving more detail. So for any vectors u, v, and w in the tangent space of M, SPV dot product with W is the same as SPW dot product with V. As I said, proof will be given later. Okay, so let's just keep in mind this lemma. So today our main topic is normal curvature. We know what's curvature of curves, space curves. This will be basically curvatures of curves on surfaces. All right. So let M be a surface and U an orientation on M. So it's a field of normal vectors, a choice of unit normal vector field on M. Okay, say on M. All right. Our first observation is the lemma. If alpha is a curve, is a curve in M and M is a surface in R3, then the conclusion is the acceleration vector dot product with the normal vector is the same as the shape operator evaluated on alpha prime, the velocity vector, dot product with the velocity vector. Here, this is at the point, of course, alpha t if you want. We will not usually put alpha t here, but all this happens at the point alpha t. Okay, here is the proof. So let me just draw you a picture. So this is the curve alpha, and suppose we are at the point alpha t here, and this lies inside a surface. Let me draw the surface, let's say, okay, surface M, and here is my velocity vector alpha prime t, and then here is my normal vector to the surface u, and let's say this is the acceleration vector alpha prime t. Okay. This is the statement. Let's see the proof. Wait a minute. Let me change the color to black. Well, the proof is very simple. Uh, since alpha t is a curve in M, alpha prime t is always a tangent vector to the surface for all t. Well, this means hence alpha prime t dot product with u is always 0 for all t, because this is a normal vector. I should write actually u of alpha t, u of alpha t. Okay, here this is, maybe I should also change this. So everything happens at the point alpha t. So this is the normal vector at the point alpha t. U of alpha t. Okay. Well, then as usual, since we are in a differential geometry course, we just take derivative of both sides. Take derivative of both sides. So 0 is equal to d dt of alpha prime t dot product u of alpha t. Well, what is this? This is just alpha dot double prime and then u of alpha t, and then plus alpha prime t and then u of alpha t derivative. But remember that this quantity has a name, and this is nothing but just negative of the shape operator. So this is just alpha prime t dot product the shape operator at alpha t of uh, alpha prime t. Okay. Yeah. So from this we see that the shape operator at alpha t evaluated on the velocity vector dot product with the velocity vector is nothing but the acceleration vector dot product the normal vector. And this finishes the proof. Okay, here so from this equation we see that uh, the acceleration vector dot product with ut, this is nothing but the uh, length of the component of the acceleration vector in the normal direction, and that quantity is determined by the shape operator basically. So uh, let me just write here, this is nothing but the normal component of the uh, acceleration vector alpha double prime. Okay, now here is a definition. We will give a name to uh, this quantity basically. Let u be a unit tangent vector to M at a point P. Then the quantity, then the number okay, then the number Ku, which is by definition the shape operator at u dot product u. So it is exactly this number, this object, okay, this object is called the normal curvature of M in the direction u. Okay, because you see how this is computed. All right, I'll actually explain it in a moment. Let me just continue. Remark, we have some observations. First of all, the normal curvature. So we define this quantity, normal curvature, which is just shape operator at u dot product u. This is the same thing as this, and that can be written as s of minus u, because s is a linear operator, minus u, but this is nothing but k of minus u. So the normal curvature at any vector doesn't change if you just reverse the vector, okay? The second observation is this. Let u be the tangent vector, velocity vector of a curve for some curve alpha in M, then the normal curvature along the vector u, which is this, but that can be written like this. And we just proved that this quantity is equal to this. And then you see what is the second derivative. Second derivative, length of this vector is just the curvature times the normal vector of the space curve alpha. And this is sorry, here I should have, this was dot product with u of alpha 0. All right, and then this is u of alpha 0. Right here, statement is this. Uh, Second derivative, acceleration times u is shape operator at alpha prime dot product with alpha prime. Okay. And this is nothing but k0. This dot product is some real number, let's say cosine mu, where k is the curvature of alpha t at the point P, which is alpha 0, and nu is the angle between the vectors n0 and u of P. Let's say, yeah, okay. So this is the angle between the normal vector of the curve alpha and the normal vector of the surface M. Okay. So here you see the normal direction of the curve alpha doesn't have to be the same as the normal direction to the surface, right? Normal direction of the curve alpha is of course parallel to the acceleration vector alpha double prime, but the normal vector to the surface M is this vector u. They don't have to be the same. And the angle mu is just the angle between these two vectors. All right. Okay. Here, remember, this was the principal normal vector of alpha. Okay. And up at the point P, of course, alpha 0. And this is the normal vector, unit normal vector. This is also unit. Both of them are unit vectors, unit normal vector to the surface M at P. All right. The third observation is this. Let U be any tangent vector, be any unit tangent vector to M at P, and let P, big P, the plane through the point P containing the vectors U and the normal vector UP. Okay. Let sigma t be a unit speed. Maybe I should say sigma s be a unit speed parameterization for the intersection curve M with the plane P. Okay. Since of course sigma s is in P for all s, wherever it is defined for all s, let's say both the tangent vector and the normal vector lies in uh, P. So this is the plane curve, therefore its principal normal vector and the principal normal vector of sigma s lies in P, and thus this vector uh, n of alpha p, n p should be plus minus up. Why is that? Let's see why this is the case. Let me just draw you a picture. Okay, let's say this is the plane P, and this is cut by a surface okay, and here is yes, so the intersection curve is something like this. Let's say this is sigma, and at a point here P, so my normal vector to the surface is this. This is n P, and my tangent vector is U. Okay. So both of these vectors, both NP and U, lies in the plane U. Uh, and I know that uh, the normal this vector and u are in the same plane, uh, and u also lies in this plane. Therefore, the vector u, right? Uh, you see, P is the plane containing the vector u and up, right? P be the plane through the point P containing the vectors u and bq, and uh, okay. Uh, okay, and so here is the situation. U is perpendicular, so UP is either like this or like that. And here is what happens. Let me write in more detail. Uh, so UP is perpendicular to uh, little u, because this is normal to the surface and u is a tangent vector, since u is a tangent vector. And I know that np is normal to u because this is the principal normal vector. But we are in a plane P, and I have three vectors. Two of them are parallel to u. Therefore, these are either parallel or have the opposite direction. And since they are both normal, we have either they are the same or one of them is negative of the other one. And here we note that the acceleration vector is, of course, the length of this vector is just the curvature, and the uh, direction of this is the principal direction and 0. So k of u is then, which was this, and this is just the curvature of the plane curve sigma times the normal vector, dot product of up. And since these are either equal or one of them is the opposite of the other one, this is plus minus 1. Therefore, this is just plus minus the curvature of the curve sigma. Okay. So the normal curvature uh, can be is equal to the actually curvature of a plane curve. That plane curve lies also on the surface M. Now here are some easy observations. Okay. First one is this. If k of u is positive, well, we know that curvature is always positive. Curvature of a space curve is positive because this is the length of the second derivative, right? This is just the length of this vector. So in this case, if this is positive, then this should be plus 1, and this means they are the same. So the normal section sigma is bending toward UP at the point P. So what we mean is this. The normal section is why do we call this curve the normal section? Because I have the surface M and I cut this surface by a plane which is normal to the surface. That's why we call this a normal section. And here it says the following. If the curvature is positive, then this curve is bending toward the, to the normal vector. So this is the normal vector, UP, and the curve sigma is bending around this UP. Okay, if this is positive. The second observation, okay, before I do this, let me write one more sentence. In other words, another equivalent statement is this. In the direction U, the surface M is bending toward the vector UP. All right. The second observation is this. Okay. If this time the normal curvature is negative, then and 0 must be negative of the normal vector. So the normal section sigma is bending away from UP at P. Thus, in the direction U, M is bending away from UP. So this means the following. Uh, if the curvature was negative, then this surface wouldn't be like this, but it would be uh, the other way around. So it's like, the normal vector is upward and the surface is bending away from the vector u. If curvature is 0, then of course uh, this should be 0. The normal curvature, if normal curvature is 0, then the curvature of the normal section is 0. And well, in this case, this is not defined. Is not defined. All right. Hence, the normal section sigma is not bending at sigma 0, which is P. Here is an example. Consider the surface M given by the equation z equals xy. So here is my surface. Let me draw. Okay. Suppose this is the point 0, 0. Now we have four different normal sections. Well, we have infinitely many, but I'll draw four of them. One of them is this. The other one is this. Let me call this sigma 1. This is sigma 2. And then sigma 3. And then there is this section sigma 4. Okay, what are these? Let me just tell you what they are. So first one, sigma 1, this is just M intersection P, and uh, let's say P1, this is the surface P1, and P1 is the surface, sorry, is the plane given by uh, y equals minus x. In this case, sigma 1 is the curve given by z equals what? Since y equals minus x, z equals x squared and y equals minus x. So these two equations define the curve sigma 1. It's a plane curve, and in that plane it's actually a parabola. So it is this parabola sigma 1. And from this picture we see that the curvature is actually negative. So here uh, this is the point P, and the surface here is bending uh, away from the normal vector. Here the normal vector is like this. So sigma 1 is uh, so let's say the normal curvature is negative in this case. The second one, sigma 1 is M intersection with the plane P2. P2 is the plane given by y equals x this time. So my curve sigma 2 is given by two equations. Z equals x squared and y equals x. So it is this curve, okay, this curve sigma 2, and this time the normal curvature is positive. For the other two curves, sigma 3 is given is a line, is a line. This is the line given by z equals 0 and x equals 0. And sigma 4 is also a line given by z equals 0 and y is 0. So actually sigma 3 is the y axis and sigma 4 is the x axis. And since these are lines, the normal curvatures, so in this case, in these cases, the normal curvatures are 0. Both of them are 0. Okay. These two lines lie on the surface, and of course a line is not bending at all, therefore normal curvatures in these directions are 0. Okay. Okay. Here is a definition So here we have seen that normal curvature can be positive, negative, or zero. Now we will define the extreme values of these curvatures. Let P be a point of a surface M in R3. The maximum value, maximum and minimum values uh, of the normal curvature function Ku of M at the point P are called the the principal curvatures of M at P, and uh, are denoted K1 and K2. So K1 is the maximum, K2 is the minimum normal curvature. The directions in which these extreme values are obtained are called the principal vectors of M at P. Okay. Well, you may wonder why, these maximum and minimum values exist, right? The reason is the following. You see, uh, if you are at a point P, then the unit tangent vectors at this point, forms a circle actually. They can be parameterized by a circle, okay, which is a compact subset. And we will see that actually we have seen from the definition the normal curvature uh, function, which is just the dot product of the shape operator with the vector. It's a continuous function. Okay, here u can be seen as a point on the circle. So the values, so normal curvatures are just the values of a continuous function on a compact set S1. Therefore, it has a maximum and minimum. Okay, so maximum and minimum always exist on a smooth surface. Okay, here is another definition. A point P of M is called umbilic, provided that the normal curvature Ku is constant on all unit tangent vectors u at the point P. So if the normal curvature function is constant at the point P, so if it takes the same value at all points, then we call that point an oblique point. Let's see some examples of all these quantities we have defined so far. Suppose sigma is a sphere of radius r, then we have seen that the normal curvature at any point is 1 over r. Okay. Uh, we have seen that the normal curvature at any point P and at and along any direction is minus 1 over r. Okay, so if we have a sphere like this, and if you're at a point, uh, normal, how do you find normal curvatures? So you give me a direction, tangent direction, let's say this vector u, and then we consider the plane which goes through this point containing this vector, and it should be normal to the surface. It means that actually it contains also the line joining this point to the origin. So it is the normal section of the sphere, normal section of the sphere with a plane, normal plane containing this vector, and the intersection, the curve sigma, is nothing but a great circle of radius r. Okay, so this is a circle of radius r, and we know that for a circle of radius r, the curvature is 1 over r. Uh, but uh, the shape operator was we put minus sign in front of the in definition of the shape operator. Let's see. Let me remind you. So shape operator was minus, okay, at any point u was this. So this quantity is uh, 1 over r. Okay, you take also dot product with u, but since we have minus sign, it becomes minus 1 over r. All right. Okay. Uh, Here is a theorem which explains many things. Okay, let me state the theorem, and then I'll prove it in the next lecture. It has two statements. If P is an oblique point, so if the curvature function is constant of M of surface in R3, then the shape operator S at P is just the scalar multiplication uh, by the constant K, which is equal to K1 and K2. Since it is oblique point, the shape operator is constant. The normal direction, the normal curvatures are all constant. Therefore, the minimal and maximum normal curvatures are the same. And in this case, our shape operator, which is a linear operator, and it becomes a diagonal actually operator, which is just identity times the real number k. The second part is this: if P is an unoblique point, so if the normal curvature function is not constant, then of course the minimal and maximal values cannot be the same, and there are exactly two principal directions. One is giving the minimal, the other one is giving the maximal uh, curvatures, and these directions are orthogonal. So the directions along which the surface is bending the most and the least uh, should be necessarily perpendicular to each other. Okay, if the surface is bending uh, the most in one direction, the direction it is where the minimal normal curvature is minimal should be perpendicular to this direction. So it's like this. Okay, maybe I should draw it like this. Say, yeah. Okay, one of them is this. This is, let's say, where the curvature is minimal, and this is the direction where the curvature is maximum. And the vectors, so this is the vector, let's say u1, no, u2, and this is the vector u1, and they are perpendicular to each other. So here k1 is positive and k2 is negative. The surface is bending the most in this direction at this point, and it's bending the least along this direction. Okay, and the theorem is telling us that these two vectors u1 and u2 are necessarily orthogonal to each other. Note that this is a non-trivial observation. And furthermore, the statement the theorem uh, claims the following. Furthermore, if E1 and E2 are principal vectors, so let me say, so these are my E1 and E2. Okay, in these directions, then S of E1 is just K1 times E1 and S of E2 is just K2 times E2. All right, so this is the statement. I'll prove it next time. And the crucial information we use in the proof is that the shape operator is symmetric. Okay, that follows from the lemma I stated at the beginning of today's lecture. All right, let's stop now. I'll see you next time.